All right. Hello and welcome to another physics video lecture. Today we're going to be talking about optics and lenses, which is some fun stuff to talk about. All right. So let's start off here with a pretty interesting and easy question. Why do we see ourselves in mirrors? Okay. What's happening here? Okay. So the question here is what's happening to the light that's coming off the mirror? Is it being reflected or being refracted? And as you know, it is. Very good. That light is being reflected off, okay? So we have an object, which is you, and you have an image, which is the thing you see in the mirror. The closer you get to the mirror, the closer the object gets, and the farther away you get, the farther away the object gets. Now, this probably isn't blowing your mind at all, but we're gonna talk about why this happens, okay? So the reason this happens is because there are two types of images, all right? Now, what's actually physically happening in the real world is there is a light source, right, that is bouncing off of the mirror and going into your eyeball, right? For example, light bounces off of you and then that goes in your eyeball and you see yourself in the mirror. This is what we call a real path of light. This is actual light bouncing off of an actual mirror and going into your actual eyeball. These are the actual rays of light. But what you're seeing is on the other side, and what you're seeing is what is called an imaginary ray, right? That thing that's in the mirror isn't really real, which you probably knew. And we call this a virtual path. And the virtual path is what is interpreted by our brain, and it's why we see things in a mirror. That's pretty interesting. So let's talk about those two types of images. Again, the first type of image is called a real image. And real images come from the fact that actual light converges or comes together, we'll come back to that, to form an image. Okay, real light is coming together. And the best example of a real image is one that you're looking at right now. Projectors make real images. We know that they are real because if I stand in front of them, the image is still projected on me. I can make it, bigger or smaller if I want to, or I can make it out of focus or in focus. Real images you can play around with, all right? The other type of image is called a virtual image. And a virtual image only makes you appear to think that light is converging. But virtual images, there's no actual light coming together. It's just this, I don't want to use the word, it's an optical illusion that is happening in your brain that is making your brain think that you're seeing light converging in front of you, right? And the example here is a mirror, okay? Mirrors make your brain think that they're seeing images. Now again, the big difference between the two is that a virtual image you can stand in front of, you can move around, you can shine it all over the place, and you're actually moving real light that is actually shining on a surface. A virtual image like a mirror or a really still pond, okay, you can't shine that around. This is just so happens to be this trick of light perfectly bouncing off of an image and letting you see it. So we're going to come back to these two things. But again, real images is actual light converging. Virtual, like virtual reality, it only appears to come together. This stuff in the parentheses we'll talk about here in just a moment. So let's talk about the two types of lenses, all right? Hopefully you remember these from like middle school, but if you don't, we'll talk about them. We have convex and concave lenses. How do you remember them? Here's how I remember them. Concave lenses cave in the middle, they cave in, and convex lenses do the opposite. That's how I remember them. Okay, concave lenses cave in, convex lenses bulge out, and they do two very different things to light. Convex lenses do something called converging light. And this is a great word. To converge means to come together. So convex lenses take light and bring it together at a point. If you ever played around with magnifying glasses in the sun, trying to burn pieces of grass when you were younger, one, be careful. Two, that was a convex lens. It brings the light together to a point, right? Concave lenses do the opposite of converging, and they diverge light, okay? And diverging spreads light out, okay? So if you have a flashlight at home where you can change the setting and spread the light out more, those are concave lenses, right? So this is very important. Now, let's talk about what is going on inside of our eyeballs, all right? So inside of your eyeball, sitting in that hole, right? You have your little hole right there. This right here is called your pupil. That is the hole, the little black spot in the center of your eye, which lets light come in. Now, when light goes into your pupil, it hits a lens, like a real lens. It's actually this hard little disc of tissue, okay? Of connective tissue. And this lens is shaped in a way where it bulges out in the middle, which means it is well, it's a convex lens. And it causes the light to come together right there, and then it flips upside down, and that light shines on the back of your eyeball on something called your retina, which is full of all these little nerve cells, which then send that information to your optic nerve, which sends that information to the occipital lobe in the back of your brain, and that's where it's processed as an actual image, which is nuts and really cool, and a whole lecture in and of itself. Okay, but we're not going to focus too much on that. If you do, you should take anatomy and physiology. We talk all about it. It's awesome. But some people aren't able to properly have that image hit their retina, and there's two situations where we need to add an extra lens here. All right. The first situation is called being nearsighted, which is what I am. And if you wear glasses, there's a 99% chance at this stage that's what you probably have as well. And there's nothing wrong with that. But what's happening here is if you're nearsighted, you're only able to see up close, right? You can't see far away. If I take my glasses off, I can't see really much past about, I don't know, right there. I'm very nearsighted, okay? And what's happening is that when light goes through the lens of your eye, it's focusing and coming together, okay, not on your retina. It's coming up in front of your retina, right? So what do? Well, you need to have a convex lens to spread that light out so it goes farther back and hits your retina. And then different lengths, thicknesses of lenses. That's why when you go to the doctor, they're like, better one, better two. They're just different thicknesses to make sure that that light is perfectly focusing and hitting your retina. Very cool. I am wearing concave lenses right now. Did I say convex? This is a concave lens. Look at it, it caves in. If you're nearsighted, you wear concave lenses. Cool? Now, if you're farsighted, which at this stage you're probably not, you may be, that means that you can see far away, but you can't see up close. This usually happens to people, when they get older, and this is what reading glasses are, okay? Now what's happening is that now the light is actually focusing past your retina. So when it hits it, it's all unfocused and blurry and not great. So what do we need to do? Well, we need to bring that focus back a little bit, which means we need to tighten this up. So we are going to use a convex lens, which brings that focus up so it hits your retina properly. Very cool. Now, we are going to talk about lens equations, okay? And when you understand this, there's a few points that we need to see. So on this side, we're going to have an object, then we're going to have a lens, and then there's going to be an image that's created on the other side of the lens. Think about it like this. This is the inside of the projector, okay, that shines light through the lens. And then on the other side of the projector, it's making the image here, all right? So first thing we need to understand is that every lens has a focal length. It's like the defining thing of the lens, okay? And it's how far away from the lens something comes into focus, okay? Now, equally as important, okay, is now this 2f, okay? As you see, we have a focal point and a 2f. 2f is just twice the focal length. And you'll see that this is a very important number on both sides of this lens. So on this side, we have the object, okay? Let's say this is a candle, all right? So we have a candle here. That candle has a height. We call that HO for the height of the object, or object height. And it has a distance from the lens. So here's the object, and here's the lens. We call that DO, or the distance of the object. Okay? So if we have an object, we're going to have an image that's created on the other side. So again, I have my light source here. It's going through my lens, and it's going to make an image on the other side. Now that image may be what's called inverted or upside down. You may have heard this. This is actually what's happening in your eyeball. When light goes into your eye, it converges and flips upside down. So what you see is actually hitting your retina upside down, and then your brain is able to process it and flip it back right side up, which again is pretty cool. But over here, we have our image, and our image has a height, which we call HI, image height. And if it has a height, that means it also needs to have a distance, which we call the image distance. All right? A lot of stuff going on there, but that makes sense, right? Okay, so usually in class, this would be the point, and we'll do this in class, where I have you go to this cool website and you play around with this PhET Lab, which I can show you right here. And what this PhET Lab does is it lets you take your object and move it around. You can make your object whatever height you want. You can move it towards the lens or away from the lens. And what it does is wherever you put the object, okay, it shows you where the image is going to show up. All right. Now, again, what we'd usually do is do a little PhET Lab, which I will. And we would fill this out together, but I'm just going to go through it with you because, again, you know, things are different this year. So, what you're going to see are these different characteristics. Okay, the first characteristic is the image nature. And what this means is it a real image, meaning there's actual light coming together to make an image, or is it a virtual image? Okay, and it just seems like there's an image. That's number one. Number two is how big the image is. And all we care about is it bigger than the object, smaller than the object, or the same size as the object? We have the image. Oh, look at that. My actual real image is messing with me right now. Come on, real image. You can do this. Be a dude. Come on. Please. Pretty, please. Go figure that in the middle of the optics, my optics screw up. Okay, we have the image orientation, okay? And what this means is the object inverted or upright? So in this case, you see that the object is above the line, but the image is flipped upside down, okay? This would be an inverted image, okay? It's upside down. It's not going the same way as the object. And last but not least, the object location, and I'll show you how to define that. So let's go through a couple of these together. But the main point that you need to understand as we see all these, okay, is when the object moves towards the lens, okay, the image moves away from the lens and gets bigger. And when the object moves away from the lens, the image moves towards the lens and gets smaller. So again, I can kind of give you the gist of that right here. So see my object? Look at what happens as I move it away from the lens. I'm going to keep it the same height. As I pull it back, so look, watch, I'm going to start here. As I pull it, here's the lens. As I pull the object away from the lens, look at the image. The image is going towards the lens and getting smaller. Whereas when I move the object towards the lens, the image moves away from the lens and gets bigger, even though it's flipped upside down. Okay. So what you would see here is the following. If the object is beyond 2f, and again, we see our focus point here is 4 and 4. So that means 2f would be, bing, 8, because 2 times 4 is 8. So here is my 2f, and my object is at 10. So if my object is at 10, what do I see? Well, I see an image that is between 8 and 4. So it's between f and 2f. I see that it's inverted because it's upside down. I see the object is 3 squares high and the image is only 2 square high. So the image is smaller than the object. And I see that it is real, meaning if you put a light source past 2f, when it shines through the lens, it'll create a real image on the other side. You'll have actual light converging right there. Okay? This 2f is special for the following reason. When you put the object directly on twice the focal distance, so again here the focal length is 4, so twice that would be 8. look at what we get. When we put the object right on 2F, here's what we get. We get an image right on 2F, it's right at 8. That is inverted, meaning it's upside down, but it's the exact same size. So this is 3, and this is 3, and it's a real image. So the 2F is really important because you get the same size image at the same distance from the lens. Everything is just where it wants to be. Go 2F. Okay? Once we move the object between 2F and F, so again, I have it right here. Remember, 2F is 8, F is 4. When I start pushing it towards the lens, remember what happens. Okay, our image now is beyond 2F. It's now moving away from the lens, and now it's a lot bigger. So again, our object's only about 3 blocks high, and our image is about 4 blocks high. So again, we're moving towards the lens, we're getting bigger and farther away with the image. If you put the object directly on the focal point, what ends up happening is the light that hits it right at this angle where nothing converges. Nothing comes together and you get no image, okay? It completely goes away. So if you put the object on the focal point, okay, that light does not converge at all. You just get parallel light sources that do not make an image. Pretty cool. And last but not least, this is the craziest one. I'll tell you what you need to know here. If you put the object between the focal point and the lens, so here's the focal point, here's the lens, we put the object right here, all kinds of wacky stuff starts to happen. What happens is that now your image is way beyond 2F, it's like way over there. It is technically upright, it's larger than the image itself, but what's happening is you're actually creating a virtual image, okay? It's not real, it's some wacky stuff going on there. We're not going to spend too much time talking about this, but if you put, the thing you got to remember is if you put the object between the focal point and the lens, you don't get a real image. You only get a real image if you're beyond the focal point. Okay, there's no image at the focal point, boom, and there's a virtual image between the focal point and the lens. All right? Okay, we'll play around with this in class. So now, the last thing we need to briefly discuss here, okay, is the thin lens equation. And this is a bit of a doozy of an equation. It uses what are called reciprocals, or 1 divided bys, all right? So your equation is 1 divided by the focal length equals 1 divided by the distance of the object plus 1 divided by the distance of the image. Now, I'm going to show you how to do this the right way, and I'm going to show you, well, just a little something special. Okay, so here we have a normal human eye has a focal length of about 0.23 meters. So here, our F, I'm going to put these over here for the time being. F is equal to 0.023 meters. We know the distance of the object. If you put a pencil 0.553 meters from your eyeball, how far is the image from the lens? Meaning, what is the distance of the image? So you got a lens, we know how far away the object is, where is the image going to appear? I can show you how to do this. So first of all, we're going to use this equation. So I'm just going to plug my numbers in. So I have 1 divided by F. In fact, let me put this down here just a little bit. 1 divided by F equals, my F is 0.023 equals 1 divided by 0.553 plus 1 divided by di. Okay, so this may look a little tricky, and what we want here is we want the distance of the image by itself. That's what we're aiming for. So the first step you got to do is you just got to do this basic math right here. And to save us a little bit of time, I did this on a piece of paper. So you punch in 1 divided by 0.23, and you get 43.48. And 1 divided by 553 equals 1.81. Okay? We still have 1 divided by the distance of the image. Okay? Now, our next move here is we got to move this number away because, again, we want the distance of the image by itself. So we have to subtract 1.81 from both sides. Right? It's positive. So 1 minus 1.81 minus itself is 0. And 4.3 minus 1.81 is 41.67, which equals 1 divided by the distance of the image. Boom, I just brought that down. Now, we need to get the distance of the image out of the bottom here. So I multiply both sides by the distance of the image. Again, whenever you want to move something out of the bottom of the fraction, this is division. So we multiply, and we always multiply by the bottom of the fraction. And this gives me, I'll bring it over here. This gives me di times 41.67 is equal to 1. And then to get the distance of the image by itself, I have to do the opposite of multiplying, which is dividing by 41.67. Okay? And 1 divided by 46.7 gives me 0.024 meters. Okay? Now, I would love for you to sit down and work through this, put the numbers in the calculator, follow through everything that I just did, and figure that out. Okay? But I am going to show you a fantastic test-taking skill. Okay? What is this test-taking skill? Oh, actually, I think I have another question. So I'm not going to go through this one. You should solve this. Maybe we'll solve this one in class. You can tell me what the answer is. But I have this little setup for you here. And what this setup is since most of the tests you take, if you are taking a test, are multiple choice, what you can do is you can plug the numbers into the equation and then see which answer makes the two sides of the equation equal, because that's what the equal sign means, right? So let me show you what I mean. Here we have a focal length of an object placed. What is the focal length? So we're looking for the focal length of an object placed 0.6 meters. So our DO is 0.6 from a lens that produces an image that is 1.2 meters from the lens. So we know our object distance and our image distance. Okay, here's the equation. So I plug my numbers in. I know the distance of the image. I know the distance of the object, right? Now I'm going to put these numbers into the calculator, and I go 1 divided by 1.2 plus 1 divided by 0.6. And again, if you want to see the best way to do this in the actual calculator, you always want to make sure that when you're adding fractions, you use parentheses. So 1 divided by, what was it? 1 divided by 1.2? 1 divided by 1.2 plus 1 divided by 0.6. All right, 1 divided by 1.2, close parentheses. Ooh, that's fancy. That's not what I wanted to do. Let me go back. So I have to go forward, then close parentheses. And I'm going to add that plus parentheses 1 divided by 0.6. I go forward and close that mamma jamma. And this gives me 2.5. All right? Notice I have 2.5 right here. So now I know 1 divided by f equals 2.5. What do? We'll take the answers and go 1 divided by each answer. 1 divided by 0.2 equals, well, let's see. Clear all. 1 divided by 0.2 is 5. That's not the right answer, okay? The next answer choice is 0.4. So I clear, and I go 1 divided by 0.4. And that gives me, ding, 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 winner, winner, 2.5. So I know the answer must be 0.4 meters because that makes, because 1 divided by 0.4 meters is 2.5. This is called the plug and pray method, or, you just take you set it up, you put the answers into the equation, and you see if it works. Now, does this always work? No, you might have to actually write down the answer to the question, or maybe the question's too complicated, but every once in a while, this is a very smart test-taking strategy if you have the time and the resources. All right, so that is what I got about optics. Again, I have another problem set up here to show you how to do it this way. Again, this time you're looking for the distance of the object. So the trick here is you have to figure out these two numbers first. Boom, boom, okay? And you have to subtract this number over to this side. Figure out what this equals, which would be 0.05778. And what is 1 divided by what equals this number? All right, guys, we'll work on this in class. I know this is a little brain bendy, but I guarantee if you give it some time, you're gonna do great. Okay? All right, guys, if you have any questions, email me or find me on Zoom. Have a good day.